Okay, this is page 3 of the final exam review. 24 says a sample of gas occupies 20 liters. You need to know that 20 liters is a volume at 1.80 atmospheres. Atmospheres is a pressure, and 322 K. K is Kelvin, which is a temperature. How many moles is the letter N of gas are in the sample? So I have P, V, T, and N, one of each. That means you need to use the equation PV equals nRT. So we can plug in our P, 1.80, times V, which is 20, equals N. That's what we're looking for. Now R, notice we weren't given R. You have to know, you'll be given these, but you have to know how to pick them. So for R, there are 3 values. 8.31, you use that one when there's KPA. 0.0821, you use that one when the pressure units are atmospheres. And 62.4, you use that one when pressure units are millimeters of mercury. There's additional units to this, but they're all the same with the exception of the pressures. So pressure is how you determine which R to use. And if you look at our pressure, it's in atmospheres. So we are going to pick 0.0821 for our R, and then our temperature is 322 Kelvin. Another word of advice, if in PV equals nRT, T must be in Kelvin. So if this had been given to you in Celsius, you would have to add the 273 to change it into Kelvin before you plug it in, or you will get an incorrect answer. This one's already Kelvin, so we just do the math. 1.8 times 20, so the left side equals 36. The right side, 0.0821 times 322 equals 26.4 N, and then we divide to solve for N. So the number of moles is equal to 1.36, just like you can see right there, the answer we got. Okay, number 25. Fold this down. Number 25 says a gas sample is held at constant pressure. Constant pressure means that it's not changing. The gas occupies 2.36 liters, that's the volume, when the temperature is 41.6 degrees Celsius. That's a temperature. Determine the temperature at which the volume of the gas would be 3.45 liters. So notice we have 2 V's, 2 T's. So my first V and T are 1, the second are T2 and V2. So we know that we need to use the equation P1 over V1 divided by N1 T1 equals P2 V2 over N2 T2. Now, we don't need to use all of this. We only have volumes and temperature, so we're going to get rid of pressure and moles on both sides. Then we can plug in what we know. So, V1 is 2.36 liters divided by T1, which is 41.6 Celsius, but remember, with gas law equations, temperature must be in Kelvin. So 41.6 plus 273, 314.6 is actually what I plug in. Notice that this is not the same as this. That's because I added 273 to get this number here. Okay? Then my V2 is 3.45, and we're solving for T2, so we need to cross multiply. So we multiply the two numbers that are diagonal from each other, and then we divide by the one that's diagonal from our unknown. And that gives us an answer of 459.9 degrees Kelvin. So because we converted this temperature to Kelvin, the answer I get is also in Kelvin. Now the reason this says or is because if I subtract 273 from this answer, then we get 186.9 degrees Celsius. So it depends. Remember, your final exam will be multiple choice. Read the question carefully. If it does not ask you to change it back to Celsius, you don't have to. Just look at the units in the answer choices when deciding which one should be the proper answer. 26. So it says a pressure of 1,245 millimeters of mercury corresponds to how much kPa. This is a pressure conversion. I have millimeters of mercury. I want to get rid of millimeters of mercury. I want to find kPa. The conversion factors you need are 1 atmosphere equals 760 millimeters of mercury equals 101.3 kPa. You will not use all three. You choose the two you need. So for MMHG, we choose 760. For kPa, 101.3. There is no atmospheres in this problem, so we ignore that one. In this case, multiply 1245 times 101.3 divided by 760 gives us 165.9. My new units are kPa. Okay. 27. 27 is one of the easiest problems. Do not get it wrong. 27 says a gas mixture at a total pressure, you must read carefully, of 1,130 millimeters of mercury contains NO, CO2, and O2. If the partial pressure of NO is 470 millimeters of mercury and the partial pressure of CO2 is 290 millimeters of mercury, what is the partial pressure of oxygen? So we have all pressures. Our equation is P total equals P1 plus P2 plus P3. Now, if you look very carefully, some people will make the mistake of just adding these three numbers and getting an answer. That would be incorrect because it gives you the total. The total is 1,130. It's equal to 470 plus 290 plus some other one we don't know. So we can add the two on the right. So 1130 is equal to 760 plus the one we don't know. And then we can subtract 760 from both sides. P and that's the answer you get. Okay, number 28. Number 28. Says if 0.50 moles, you have to moles is N, occupy 30 liters. Liters is a volume. At a certain temperature and pressure, what volume will 7.5 moles of the gas occupy at the same temperature and pressure? So we got two V's and two N's. We have N1, V1, V2, N2. So once again, we're going to use P1, V1 over N1, T1 equals P2, V2 over N2, T2. But notice we don't have any pressures again. We don't have any temperatures. So we plug in what we know. V1 is 30 divided by N1, which is 0.5, equals V2, which is what we don't know, divided by N2, which is 7.5. So we cross multiply the two numbers that are diagonal from each other. 30 times 7.5 divided by 0.5, V2 equals 450 liters. Alright, number 29, 30, 31, we'll just talk through those really fast. So 29 says, if the pressure in a closed container is decreased to half its original pressure, what will happen to the temperature? So you need to know how these are related. If pressure decreases, that means the number of collisions are decreasing, my molecules are moving slower. That happens at a lower temperature. So these are directly proportional. Number 30, in an inflexible plastic container holds a gas. If the temperature is doubled, if something doubles, that means it's going up. What will happen to the pressure? Well, they're opposite. So, I mean, they're directly proportional. So if the temperature goes up, then the pressure also goes up. So notice if they both go down or they both go up. Number 31, a balloon is filled with gas. If the pressure is kept constant and the container is heated, what changes occur? So I'm filling it with gas, which means I'm putting more moles inside of it. The pressure is not changing. The temperature is heated. Temperature is going up. If temperature goes up, then the size of the balloon must also go up. Okay. Number 32. So I have 125 milliliters. That's a volume of a 10.6 molar solution. That's molarity, big M. Be careful. Little n is moles, big M is molarity. 200 milliliters. Just kidding, you can't see any of this. 200 milliliters is another volume. It says, what is the final molarity? Two V's, two M's. The two that go together are V1 and M1. Then we have V2 and M2. On your equations that you're given, you'll have M1 times V1 equals M2 times V2. You plug in what you know. 10.6 times 25 equals, well, we don't know that one, times 200. So I can multiply the two numbers on the left and then divide by the 200 on the right, and the mu molarity is 1.325. Okay, we're almost done. Number 33. What is the molarity of a 0.25 liter solution that contains 75 grams of CaNO3? Okay, so it says, what is the molarity? You have an equation that says molarity is moles divided by liters. We don't have moles, so we need to convert our 75 grams of CaNO3 into moles. We've done this plenty on the previous page. So we have grams of CaNO3 is equal to 1 mole. So we need to find the molar mass to put right here. You get those numbers from the periodic table, you add them all together, and you get 164.1. So now we divide 75 divided by that, gives us 0.45. So we can plug that in here for moles, 0.45 moles divided by our 0.25 liters that we were given in the problem. 0.45 divided by 0.25 is molarity equals 1.8. Okay. And this last section, soluble or insoluble, you will need to use the backside of this periodic table. So notice there's a soluble section and an insoluble section. So if we look at, let's see, get this right there. So if we look at the first one here, it says NaBr. So we're going to look for the Br. So we find Br. Br is in the soluble section. There are 3 exceptions, but Na is not one of them, which is why NaBr is soluble. That's an S. We look at B. It says Ca3PO42. So we're going to look for the PO4. The PO4 is in the insoluble section. There are some exceptions, NH4 and group 1 metals. Group 1 metals are the elements in group 1 on the periodic table here, right? Li, Na, K, Rb, and so on. Well, Ca is not a group 1 metal. So we turn this back over. We see PO4 is insoluble. Ca is not an exception. So that tells us that this is insoluble. For letter C, we have BaSO4. We're going to look for the SO4. So SO4 is the last one in the soluble list. And so we find SO4. There are some exceptions. Ba is one of them. So even though SO4 is soluble, there is an exception of Ba. So that makes this insoluble. It flips to being the opposite when there is an exception. And then in letter D, KOH, we find OH. OH is in the insoluble list. There are a number of exceptions. K is a group 1 metal. If you turn the periodic table over, you'll see that. And so because OH is insoluble, but there is an exception, it flips to being the opposite, and so it is in fact soluble. Alright, so that concludes page 3 of the review.